Hello, I am Major Jeff Choate, a PhD candidate at the Air Force Institute of Technology. This video is meant to complement the journal article submitted to the Advanced Intelligent Systems Journal. The work is titled From Simulation to Reality, Transfer Learning for Automating Pseudo-Labeling of Real and Infrared Imagery. Our work is focused on the problem of automating aerial refueling. Here we must find where objects are within an image. We are focused on using only cameras to make these predictions for three large reasons. First is because existing aircraft already have long-wave infrared and electro-optical cameras on board. Second is because as military, we do not want sensors whose emissions can reveal our location. And because additional sensor suites would be expensive to implement across existing fleets of aircraft. In past work, we have shown our system using a convolutional neural network and the solve-P&P algorithm can make position and orientation predictions for aircraft and drug baskets within color imagery. However, transfer learning from simulation to reality has proven difficult. This is because any simulation is not a perfect representation of reality, and because we lack the ability to simulate the appearance of objects viewed by long-wave infrared cameras. An obvious solution to improve performance is to train the CNN on data closer to the target domain, i.e., using labeled real flight imagery from operations. However, creating labeled data of real imagery is difficult. This is because manually labeling real imagery is imprecise and extremely time-consuming. Also, using a neural network to assist with labeling may result in false positives if tuned too leniently, and result in false negatives if tuned too strictly. Thus, we ask the question, can we synthetically train a CNN precise enough for our larger system to label the real images? Can we apply that solution to wavelengths we can't simulate? If we train on that labeled imagery, will performance of our system increase? And does the camera calibration affect this labeling process? Our proposed system will be shown by various experiments and real-world flight tests to address these questions. To summarize our past work regarding how we create the high-quality, precisely labeled synthetic imagery, first we take a 3D model of an object in our OpenGL software called Afterburner and define components of the object by creating point clouds on the object. Screen space, creating bounding boxes around them. Then expand those bounding boxes to correct for perspective distortion and ensure the 3D geometric center matches the bounding box's center. And we repeat this process for 10,000 training images, where we randomize positions, lighting, and background environments, creating enough images to train a YOLO version 5 small network. In order to show this, neural networks were trained to detect parts of three different objects. First is the color imagery of the drogue basket viewed from the front. Next is the drogue basket viewed from the back. Finally is the imagery of the Learjet. Drogue from the back in the Learjet grayscale instead of color to better simulate long-wave infrared of the real-world flight tests. Thus, we have three CNNs trained on purely synthetic data. We use these networks as part of the larger system to make position and orientation predictions of the December 2023 flight test imagery. These position and orientation predictions can then be used to label the real images. This process is to take the real image from the flight test, have one of the neural networks make bounding box predictions on it, and utilize the bounding box predictions and solve-P&P algorithm to find a position and orientation of the object, and then use the same process as earlier to reproject those point clouds, defining components of the objects back to the screen to make new bounding boxes for. What this means is that a CNN which finds only four bounding boxes of an object, solve P&P can find a pose for that object, and all components of that object can have bounding boxes created for it, even if partially occluded. Here we see that process in action. On the left are green bounding boxes, indicating the predictions by the YOLO version 5 CNN, and on the right are the newly created labels from the solve P&P pose predictions being reprojected back to the image. The snippets of video here were chosen to show periods where the performance was mediocre, showing that the prediction ability of the CNNs degrades when the drogue is in front of the aircraft, and the solve P&P estimates can jump around when too few bounding boxes are predicted. These plots show how well our initial networks performed. They made many good estimates, but they obviously made estimates that were bad as well. Hence, to ensure a system trained from these labels will perform well, one should first attempt to filter the outliers. The table shows the criteria used to determine if an observation was an outlier and indicates how many images were left of the good observations after an 80-20 validation and training split was done. To tune the confidence, we viewed videos of CNNs predicting bounding boxes at different confidence levels to observe which confidence presented enough true positives and few enough false positives to make a fair number of good pose predictions. Furthermore, we knew the parameters of the flight test. For instance, we knew that the drone was never closer than 3 meters or further away than 50 meters for the color imagery. Hence, we can discard observations which estimated values outside those ranges. After this filtering, a large set of imagery was left over and split into training and validation datasets for the daytime flight test. It is worth noting the tanker aircraft had a left and a right long-wave infrared camera on each flight. Only the left camera was the source for training and validation imagery, or the long-wave infrared CNNs. We also calculated the reprojection error as a filter. This is the average 2D Euclidean distance for the bounding box centers between their YOLO bounding box prediction and the pose reprojection back to the image of those same bounding boxes. Finally, even though solved-PNP can make pose estimates when provided with only 4 points, its behavior with 4 or less points was frequently bad. Hence, those were discarded as a rule here. Thus, the filtered training images were then combined with the synthetic imagery used to originally train the CNNs, and each of those original CNNs was further trained for another 100 epochs with a patience of 20. None of the patience criteria triggered. Looking at results for the color imagery, we can see that the system using the retrained network marginally increased its performance over the system with a purely synthetic training. Also, our networks were compared to a network which used a hybrid training approach with real precisely labeled imagery from a motion capture room and simulation data to train a CNN, and our networks outperformed that network during the daytime. But retraining was required for our network to outperform that network during the night. Here, one should not compare the prediction count number from the motion capture network and the networks trained herein, because that network had a larger number of components defined on its drogue model. The EO network did very well on the real data initially, so there was not much room for improvement. However, the charts here show the performance did increase across all metrics, and with this retraining, it was able to outperform a network trained in the motion capture room on real and synthetic imagery. The upcoming video shows that this retraining also allowed the CNN to be performant as the drug was leaving the scene, where it previously failed. The retraining technique truly excelled when we applied it to the long-wave infrared imagery. Here we see multiple pixels of reprojection error before retraining, but after retraining it gets reduced to nearly under a pixel. This is also seen by an across-the-board increase in the number of bounding boxes that are predicted for the networks, the number of good pose estimates made, and the decrease in bad pose estimates that are made. This video shows the old neural networks on the top left, their pose predictions being reprojected to the image in the top right, and the retrained networks and their pose prediction reprojections on the bottom. Here we show the same scenarios as before, where the network would struggle, but now is very steady pose predictions. Here we demonstrate the increase in performance of retraining. These plots show the dataset for the night flight of the right long-wave infrared camera mounted on the tanker, and the drogue network making predictions on that data. It is worth noting that this imagery appeared slightly out of focus and blurry. Thus, it is sensible that the network performed so poorly, as seen on the left, with a large number of bad pose estimates and various periods where it failed completely, and this is before retraining. But after retraining, hardly any false positives are noted, and no obvious periods where the network completely failed. Another experiment was conducted to identify the importance of a precise camera calibration and camera intrinsics. Here we used the CNN trained on synthetic imagery to predict bounding boxes for the daytime color flight test. Then we sent those bounding boxes to perspective endpoint with a variety of different camera intrinsics. Those same intrinsics were then utilized to reproject all object components back to the image to create bounding boxes. The plot compares each set of intrinsics to a base case intrinsic, calculated by using the checkerboard calibration technique in OpenCV, seen as the gap in the red line. The focal length was varied as observed through the x-axis in the plot. The red line represents the center point CX/CY intrinsic value calculated with the checkerboard calibration, while the blue line represents an assumed perfect CX/CY value. Across all reasonable values of the intrinsics, we observe less than a pixel of reprojection difference, indicating that it is not important to have a good camera calibration to perform our relabeling technique. This means a user of our technique could apply it to old datasets where they have no idea what the camera calibration was, and even datasets that used multiple cameras. Thus, we have answered the questions we set out to. Using our post-prediction process, we can label real imagery. That labeling of real imagery can then be used to train a system to make better post-predictions. This technique is even able to allow a user to bridge the gap from synthetic imagery to real imagery. Real imagery we are not able to realistically simulate. We showed this with simple grayscale images transferring to real long-wave infrared images, training on them, and then having robust performance on that long-wave infrared imagery after retraining. Finally, we showed this is not important to have a precise camera calibration to do this relabeling. It is worth noting that the precision of the camera calibration will directly affect the precision of the pose estimate, but this is immaterial. The goal is to simply label the imagery. In the future, we expect to apply this technique in flight tests with better sources of truth, which can then be used to verify the precision of the bounding boxes and the precision of the pose estimates by the system we create. Additionally, the techniques herein use very simple filtering of observation. More advanced filtering techniques like Kalman filters can be applied to time series natures of our application domain, and this can be applied to both the 2D bounding boxes and the 3D pose estimates. With this, we can make our overall system much more precise in the future. Thank you for taking the time to view our research.